All right, thank you everyone for coming. I also especially want to thank the organizers of this session. I've really enjoyed the talk so far, and also hi to, I know we have several dozen people looking at us through the web. So I'm going to talk about air pollution, weather, and human health under a changing climate. Am I? Maybe I'm not. All right, and here are the topics today for the presentation I prepared for you. I'm going to talk about a couple of the key ways that climate change could impact human health through atmospheric systems. One is through changes in tropospheric ozone, which is a common air pollutant that harms human health, and the other is through weather-related health and climate change, where I'll be focusing on heat and heat waves. I want to emphasize early on that these are just two of the many different ways that climate change could affect air pollution or weather and thereby human health. I'm also going to talk about an issue that was brought up earlier today of co-benefits, co-costs, because it links very closely to the issues of climate change policies versus air quality policies. And then I have a few concluding thoughts. So let's start by talking about tropospheric ozone and human health. I believe it's critically important to do the best we can to understand how these environmental stressors impact human health in the present day. In fact, I would argue that if we don't have a good handle of how these relationships are in the present day, we have a very limited ability to look at these issues under a changing climate. Further, as has also been mentioned today, many, and I would argue most, of the environmental health issues from climate change are not new problems, but are exacerbations of existing environmental health issues that we have today. And certainly the ones that I'll be talking about fall into that category. There has been a wealth of literature showing us that exposure to tropospheric ozone affects your human health in many different ways, including an increased risk of hospital admissions, premature mortality, respiratory symptoms like coughing and wheezing, reduced lung function, and many more. And we also know that these effects are not uniform across populations. There are different effects in different types of communities, different age groups, such as higher effects for the elderly, and so on. I also want to emphasize that this is not a small problem today. This is a map just for the United States showing you areas where people are living in locations that exceed the EPA health-based standard for tropospheric ozone. This represents over 100 million people in the United States. So that's today, before we get to a changing climate for future conditions. This is not just an issue for more developed countries. In fact, a lot of areas have a growing problem for ozone due to expanding transportation systems and growing industry. So this is a very important environmental health issue today, even if we weren't going to talk about climate change. But since we are interested in talking about climate change, this is also one of the areas that has been recognized by many different agencies and scientists as a critical environmental health need. Just to show you one example, this is a report from the National Institutes of Health looking at a human health perspective on climate change, and they highlight the potential for tropospheric ozone and many other air pollutants to harm health under a changing climate. And here are just some of the human health responses that they list as potentially impacted by increased levels of ozone from a changing climate. So basically the same health outcomes that we would see for ozone today: asthma, other allergic diseases, chest pain, coughing, reduced lung function, cardiovascular disease, and so on. Now, how does climate change affect ozone? And this is interesting because there are a couple of different pathways, and I'll talk through both of them. Well, we could think about air pollution more broadly, that air pollution could be affected by climate change due to changes in precipitation patterns, wind speed and direction, and temperature. But also the overall higher average temperature does mean faster chemical reaction rates for tropospheric ozone. It also means more emissions of the natural ozone precursors. So let me talk about that a little bit more. I don't know if we have any chemists in the audience, but this is a grossly simplified version of tropospheric ozone formation, where ozone is not a primary pollutant. It's not directly emitted from our car tailpipes, but it's formed in the atmosphere where these ozone precursors go through photochemical reactions. And we have two types of ozone precursors here. We have volatile organic compounds and nitrogen oxides. In the presence of sunlight, form ozone. Now, the most talked about way in which ozone could be affected by climate change is the most obvious one, that increased temperatures increase ozone. This means that if the ozone precursor emissions stayed identical, no changes at all, under higher temperatures, you have more ozone produced in the atmosphere. This is why we have higher ozone during the summer periods and the winter periods, and is one of the reasons we have higher ozone during the day than at night. There's another pathway that gets a little bit less attention, which is the issue of more volatile organic compounds. So both of these precursors to ozone have both anthropogenic and natural or biogenic sources, but for volatile organic compounds, these biogenic sources actually can play a major role. And here I'm talking about the emissions of VOCs from trees. In general, higher temperatures mean more VOC emissions. So we're talking about a situation where even if we didn't change our emissions, even if we didn't have population and economic growth, under overall higher temperatures, we would have more emissions of ozone precursors from these natural VOCs and faster chemical reaction rates, producing more tropospheric ozone. I'm going to take one more slide on each of these two pathways just to talk about them a little bit more. This is just a figure showing you the relationship between temperature and ozone for New York City. Each dot is a day, and you can see very clearly how strong this relationship is, where up until a certain point there's not much of a relationship, and then a very strong relationship where higher temperatures means higher ozone. Also for biogenic emissions, as I mentioned, we have higher temperatures means higher VOC emissions from trees. Now, how much VOCs is coming from your trees depends on a lot of different factors. It depends on the type of vegetation, it depends on the health of the vegetation, but it also depends on temperature. And I want to emphasize, these are not small amounts of precursors relative to the anthropogenic amounts. In fact, for VOCs, the order of magnitude for these natural emissions can be on the same order of magnitude as what we have for the anthropogenic emissions. So this is a very substantial contributor to ozone precursors. Next, I want to walk you through a study we did looking at how ozone could affect health and could affect climate change. We looked at 50 cities in the eastern United States, and we dealt with a lot of the systems that we've been discussing today. We linked global climate change modeling, air quality modeling, meteorological modeling to estimate how climate change could affect ozone levels in the future. And we looked at two sets of time periods. One is summers during the 1990s, which we use to represent the present day, and the other is summers during the 2050s. And clearly, as we've discussed and as we all know, there's so many different uncertainties and assumptions and things to think about for what the future might look like. So we made a decision not to try to estimate what ozone would look like in the 2050s. We wanted to isolate the impact of climate change. So what we've done here is take a 2050s climate and put it on today's emissions. So we're not accounting for population growth. We're not accounting for change in technology. We're not accounting for changes in emissions. This is just isolating the impact of climate. You can think of it as taking the 2050s climate and putting it on today. So we don't have to try to set apart the different issues from, well, how much of this increase in ozone was due to population and economic growth versus how much was due to climate change. And these are some of our results. This is showing you the 50 cities in the eastern U.S. This is the increase in ozone for one metric. We looked at multiple different ozone metrics. And the size and color of the circle corresponds to the size of the ozone increase. So you can see for the pink and purple dots, we had over 10% increase in ozone, and then down to smaller increases in ozone down for the blue dots. So a couple of points I want to mention. One is, we know that this is a current problem today. So numbers that, I don't know if they seem small or large to you if I talk about a 4 or 10 or 12% increase in ozone, but this is actually a very important human health problem. So this actually represents a very large increase in an important environmental health exposure. The other thing I want to mention that we've also discussed a lot today, is one of the themes, is where do we have more certainty and where do we have less certainty in our results? So I would argue that I have less certainty in each individual city, but I have a lot more certainty about the overall trend looking across the 50 cities. And here, this is a situation where all the cities showed either a negligible difference in ozone or showed an increase in ozone. So even though we may not have certainty about some specific regional effects, we do have an overall trend in how the results turned out. This is just another way of showing the results. This is looking at the percent of summer days in air quality index categories. So this is a EPA designation where green represents healthy levels. Yellow is starting to represent unhealthy levels of ozone for sensitive individuals, moving up to orange, red, and purple, which doesn't even show up on the current day chart, showing you how we have an increase in the number of days with unhealthy ozone levels. Next, I want to talk about my second kind of case study of how climate change could affect human health through atmospheric systems, and here I'm going to talk about weather-related health. Again, this is an issue that we deal with today. So aside from any type of change in climate, we know we have a wealth of studies from many different researchers around the world showing us that high temperatures and cold temperatures affect human health in a myriad of ways, including increased risk of hospital admissions, mortality, and so on. We also know that some populations are more affected than others. And this is an issue where it's the age of the population matters, socioeconomics may matter, but we also have very strong variation in the effects by region. This is some result from Brooke Anderson, who I just want to mention also did the power outage paper that you saw earlier. And this is showing you the concentration response curve type of format for weather and health. So down on the x-axis we have temperature, and on the y-axis we have an increase in mortality. This is just using New York City as an example. You can imagine we have these different curves for other various areas. So on the right, this is the average of the same and previous day's temperature. And you can see as temperature gets higher, mortality gets higher. There's nothing special about 60 degrees. We're just showing you the high end of the heat curve and then the low temperature for the cold curve. And what's different about the blue is that it's a different time frame. It's basically the previous several weeks of temperature. So this is very important. The mechanisms through which human health is affected by weather is very different for high temperatures and low temperatures. This is also, just from a scientific perspective, a very interesting exposure because most environmental exposures, you have higher effects at higher temperatures, or higher exposures, I mean. Normally you have higher effects at higher exposures, maybe you have some threshold effect, but here you have the high exposures, here you have the high health impact at the high exposure in the very, very low exposure. So what we're interested under a changing climate is what would this curve look like in the future? Is it going to just shift all the temperatures to here? Or is the inflection point at which these curves bend going to differ? Or is the slope of this going to differ? Is it going to be a stronger impact where you have more of an increase in health for an increase in temperature, or are you going to have less of an increase in health for temperature? So getting a sense of what this curve looks like in the future is really important, not just what's the distribution of temperatures across that city. Another thing that's very interesting about weather and health that is going to be important under a changing climate is that the effects are not highest where you have the highest exposure in terms of location either. So this is some work also by Brooke Anderson looking at, this is heat-related mortality, so it's just to pull 2 points off that curve, this is your risk of mortality at 80 degrees compared to 60 degrees. So we're normalizing across all the city's different temperature distributions, and here the size of the circle corresponds to that community's certainty of estimate. So a big circle means we have a more certain estimate for that city, and a little circle means we have less certainty for that estimate. And so the reds are showing higher heat impact, and yellow are showing low heat impact. So this does not look like a heat map for the United States, where you have high temperatures down here in the southeastern. In fact, we see the highest, or some of the highest heat-related effects in the places without the high heat. This is extremely important for climate change studies where we want to think about what will this map look like in the future. And so you can imagine some of the early studies did things like take the temperature of Atlanta and say, well, the temperature of Atlanta, maybe that climate will be what we have in Boston in the future. So maybe we should take the exposure response curve for Atlanta. And so that was a reasonable approach to do early on, but we know now that there are many other things that are different. The populations are different, the housing structure is different, and has been built over decades and decades. So another assumption that is pretty bold to make, that I would argue against, is the idea that if Boston had a much higher temperature, that it could adapt in, say, a generation or in a short time frame to what happens in the hotter climates. The building structures, for example, are very different in cold and hot climates and are something that are certainly not trivial to change. This is from a study led by Roger Peng at Johns Hopkins University in the Department of Biostatistics, where we were looking at what heat waves could look like under a future climate. So now we're taking the city of Chicago, we've estimated the relationship between heat waves and mortality and hospital admissions and other health endpoints in the present day, and for this work we want to look at that mortality estimate under a changing climate. So as we've talked about a lot today and we'll continue to talk about, we have various different uncertainties along the way. So how are we going to deal with that? Well, for one thing, we have 3 different climate scenarios, so we can think of this as 3 different policy options or 3 different futures. Within each of the 3 horizontal bars, you have 7 different climate models. So we have 21 or so estimates looking at different climate scenarios and different climate models. This is showing the number of deaths we expect from heat waves per year. And here we are accounting for the change in population that we anticipate in the future. Because what we really want to do is look across the different policy scenarios and the different climate change models. One of the things that was surprising to many people who don't deal with climate change research is that the biggest uncertainty was not which policy scenario you use, it's which climate change model you use. That's this big uncertainty that you see across here, and across here, and across here. But the other key point I want to make about this that I believe strongly is that the lack of complete information is very different from the lack of any information. The fact that we have some uncertainty does not mean we know nothing. And what we are good at estimating is kind of overall trends. So looking across our different sensitivity analyses, we can see an estimated increase in the number of deaths from heat waves across all of these different scenarios. So yes, we have uncertainty across the climate models, giving us different magnitude of an increase in deaths, but giving us an increase in deaths overall across the different scenarios we looked at. All right, so the third key topic I want to hit on is this issue of co-benefits and costs for climate change and air pollution policies. And historically, people have looked at air quality policies, and by this I mean a policy designed to improve air quality in the short term, possibly designed to improve human health. So these are things like policies to come into compliance with air regulatory standards or guidelines and so on. And then we have climate change policies, by which I mean policies designed to reduce greenhouse gas emissions. But what's interesting is that many of the strategies to improve air quality in the short term and the strategies to lower greenhouse gas emissions have an enormous overlap. So you can imagine, for example, a change in transportation patterns that maybe was designed to improve air quality, but as a nice side benefit ends up lowering greenhouse gas emissions. Or alternatively, you could imagine a community working to lower their greenhouse gas emissions and having improvements in air quality in the short term, regardless of what happens for climate change. And all of these impact human health in that way. If you have this overlap in policies, they all impact human health both in the near term by improving air quality over the next 5-10 years, and in the long-term future from climate change. So historically, these policies have been analyzed separately and in fact have been regulated separately. But this is one of my favorite quotes. When we try to pick out anything by itself, we find it hitched to everything else in the universe. So I think clearly these things are very related. And some people have looked at this, and this is another situation where I feel it's important to distinguish between the lack of complete information and is different from the lack of no information. So this is a study where we did a systematic review and assessment of research that had looked at this co-benefit issue. And so I'm going to walk you through this framework. So up here, we have climate change policies with the aim of reducing greenhouse gas emissions. And this could include regional, national, or international efforts. An example might be a carbon tax. Up here, we have air quality policies with the aim of reducing harmful air pollutants in the short term. And these are some examples: changes in public transportation and vehicle fleet. Both of these could impact greenhouse gas emissions and could impact air pollution levels. The italics, if you're interested, are just some of the research techniques that people use to get those estimates. Moving down here, we have human health responses, both from the future, from changes in greenhouse gas, and from the short term, from changes in air pollution levels. And then, for some studies, take it a step further to look at an economic assessment where they are evaluating the different health impacts. And if you want to do a complete loop to look at the true co-cost and benefits, you might want to look at the economic impacts of the cost of implementing your climate change policies or the cost of looking at your air quality policies. Now, a lot of studies have looked at this issue, and the studies that we talk about that I'm going to talk about today are studies that are looking at how would climate change policies that have nothing to do with short-term air quality impact air quality in the short term, and how would that impact human health in the short term. And then a subset of the studies looked at economic impacts such as cost of illness and willingness to pay. And we found a huge variety of studies, enormous variety, looking at different parts of the world, looking at very different climate change impacts, climate change policies, looking at very different air pollutants, different ways of estimating health, and for the subset of studies that looked at economics, of course, different ways of estimating economics. We also found many different disciplines that looked at it. So there were a lot of studies from economics who had enormous detail here and quite simplistic methods for 1 and 2. Similarly, from my community, the human health community, they had enormous detail about how air pollution affects health, and then maybe some simplistic parts for 1 and 3 if they used it. And then again, the atmospheric scientist community that had the most sophisticated modeling for part 1 and more simplistic approaches for 2 and 3. Looking at different policies, different parts of the world, and so on. But these studies overwhelmingly showed a co-benefit of climate change policies on air quality. So this again, I think, demonstrates that even though we can have a lot of uncertainty, when we look at all the literature and research together, we do see some very interesting and important trends in the results. Okay, so now I just want to share a few concluding thoughts. And one is, of course, that, I've talked about co-benefits or co-costs of climate change and air quality policies. Before that, I talked about how weather could impact human health, and before that, I talked about tropospheric ozone as one of the air pollutants that could be affected by climate change and their impact to human health. But clearly, all of these are related to a lot of other issues and environmental health stressors that could result from climate change. So we've already talked a little bit about the issue of environmental refugees, such as people, by which I mean people who are dislocated from their home because of extreme environmental conditions. We could also talk about nutrition and agriculture and how your baseline nutritional status might affect how susceptible you are to air pollution or weather extremes and so on. So I want to highlight that many of these things are clearly related. And in the last couple of slides, I want to talk about some ways that we're thinking about the paths forward. As the subject of this session is emerging research, we want to think about what are some of the current research topics that I and many others are working on, and one is the changing demographics. So I mentioned for both of the case studies I mentioned for ozone and weather-related issues from climate change, that it matters who is being exposed. And for both of those cases, an example of a group that has a particularly high effect is an older population. And this is just showing you trends in the population 65 years and older. This is just for the U.S., showing you by region. And so these change in demographics, these change in who is affected, is really important because that exposure response curves that we may develop, those are typically or often developed for the population overall. If we know that relationship differs for different population, here just using age as an example, but we could also look at race, ethnicity, we could also look at socioeconomic status. If we know that those relationships and those effect estimates are different for different populations, what the population looks like in the future could matter a lot. And here I have this data that's divided up by region on purpose because we know that many of these environmental health exposures are critically different when we look at different locations. So what is the population going to look like in different regions is also something we want to think about. And then finally, the kind of big elephant in the room is the issue of adaptation. Can we adapt, or what degree to which will we adapt to climate change? I would also argue how quickly will that happen, and I would also argue how much is that going to cost. Is really important. And one of the things that we're looking at for weather-related mortality is the issue of air conditioning. And here, this gets very much to an issue of where in different parts of the U.S. and different parts of the world do people have the resources to adapt. So it's not just an issue of, is there an adaptation measure that's possible and how much will it cost? It's also who has those resources to do it and where will it not take place. This is just showing you the percent of occupied houses in the United States with central air conditioning. This is from U.S. Census data. And here, this data I pulled for different types of populations. So what's interesting is the prevalence of air conditioning for central air conditioning is quite different across population. So for example, below poverty is that lowest line right here. So the poor populations, as you would expect, have less central air conditioning. But we do see this trend with increasing central air conditioning for every demographic here, and actually every demographic that I bothered to look at in the U.S. Census data. And central air conditioning is actually a fairly recent phenomenon in the United States. What this doesn't tell us is how often that central air conditioning needs to get turned on. So here we get to one of these very complex feedback loops where if central air conditioning is used as a method of adaptation, so we have more and more central air conditioning, this is actually using energy. This does not have a neutral impact on greenhouse gas emissions. So we can get into some very complex issues when we start to look at these pieces, and that's why I think it's very useful, as was mentioned in some of the earlier talks, to have multiple disciplines looking at these together. So those are the key points that I wanted to share with you. Again, I want to thank the conference organizers and thank all of you for coming, and thank you for your time. Thanks.
Thank you so much. We have time for 2 questions, please.
Thanks very much, Michelle. This is John Balbus with NIEHS. Very nice presentation. You showed some slides. You showed a slide of the U-shaped curve of mortality in New York, and you raised the question, well, that's now, but what about the future? You showed a study by Roger Peng looking at Chicago in 2080 and projecting the mortality, and my guess is that study probably used an exposure response curve derived from current observations and did not change it. And my question is, what is the state of the art now in terms of how do we, I mean, the exposure response curves are correlational. They're not mechanistically modeled. They're based on observation, so they take into account the air conditioning, the population, the demographics, all of those things. So what would you say is the state of the art now in terms of adjusting a dose response curve? You know, what's the best example that you've seen? And what, if you could have your druthers, would you be able to do in 5 or 10 years with that?
So your assessment of what was going on in the Roger Peng study is absolutely correct. So that study, we used what I call the exposure response curve for heat waves for the present day. We did incorporate changes in population, but doesn't incorporate adaptation. And that was something that was very clear in that research project, that there are many different uncertainties, and there's actually I don't have it, but I'm glad to share it with anyone who's interested, a very nice graphical framework of the overall research vision, including that work of here are the various different uncertainties and various different issues, and we're going to basically try to pick them off one by one or as we can, and increase in population is a lot easier to deal with than adaptation. So right now a lot of work is going on to try to look at adaptation, looking at what are the long-term trends. And adaptation is not something that's just specific to the unprecedented rapid changes we have from climate change, but also due to the different ability to adapt our body to comfort for things like weather or air pollution. So there's some very outstanding work by Francesca Dominici, who's at Harvard University, looking at how environmental exposures, including weather, have changed over time in the past. So our response to heat waves today is actually less than our response to heat waves, say, a few decades ago. Another issue I want to highlight, also Brooke Anderson again, looking at these issue of heat waves, is it's not just is today a heat wave or not, but the current, what I would call state-of-the-art modeling, is looking at how different heat waves have different impacts. And this isn't necessarily just how you define a heat wave, but not all heat waves are created equal. So in the future, we anticipate that heat waves will occur more often, but we also anticipate an increase in intensity, so they'll be hotter. We anticipate an increase in duration, so they'll last longer. And they may occur at different times of the year, and there's a lot of evidence that the first heat wave is more harmful than heat waves later on and so on. So there's a lot of exciting work going on in adaptation. My personal take on this is that looking at a lot of different sensitivity analyses with different types of models is very useful, because when we find consistent trends across all those different analyses, it gives us more confidence than any single result alone.
Thank you. And the second question, please.
Yeah, hi. Lou Ziska from USDA. Thank you. That was a great presentation.
thanks.
I enjoyed it very much. I especially like the Muir quote, so let me tug a little bit on that, if you will. We see a lot of work looking at how rising CO2 levels affect plant growth, and the link with VOCs is fairly clear. Has that link, in fact, been made explicit with some of these models, so that as CO2 increases, you have greater growth, you have greater changes in the qualitative change with respect to the different chemistry, different plant chemistries? Does that in turn have a definite link with respect to the ability of trees or other plant species to produce VOCs? Has that been looked at?
So the short answer is yes, it has been looked at. And so in a lot of the air quality models and things of that nature that we use, they are accounting for differences in VOCs under different types of conditions. In terms of the details of those models and how well they represent real-world conditions, that I'm probably not the best person to ask, because I'm more a user of the model, or rather I'm more collaborate with people who are experts on that modeling systems. I haven't run the current versions of those modeling systems. My time running air quality modeling was some time ago. So one answer is yes, that is included. How accurate it is, I don't know, but I know it's something that's recognized is critically important, is something that we want to get right, especially because it affects ozone and it has enormous agriculture impacts as well.
All right. Thank you very much.
Thank you.
Thank you so much. And now we're going to move from the air media to water media. And I'd like to introduce Julie Turtan from NOAA.